And yeah, we can start the quantum seminar. We are very happy to have James Thompson here today. He did his undergraduate degree in Florida and then moved on to do a PhD at MIT in Dave Pritchett's group, where he, I think, understand that he was measuring with two different ions in an ion trap, like the energy to mass ratio, and won his thesis prize, the Damop thesis prize for it. Then he remained at MIT, or at least in Harvard, or in Boston, and went on to do a postdoc in Vladan Vuletic group. And since 2013, he is at JILA as an associate professor and as a fellow. And we are very happy to have you here. I Googled a bit around with your name, and James Thompson has a statistically significant amount of professors associated with it. So there's a history professor, a political science professor, a philosophy of language professor, a professor of finance, and a professor of urban planning with your name. So we are happy to have you, and please give us your talk.
It's clearly a distinguished professorial name, huh? That's what you're saying, huh? Great. Well, thank you for inviting me to share about some of the stuff we're doing in my lab. When I look like I'm looking away from the camera, I'm actually looking at you. You're over on my laptop. Can everyone hear me okay? Am I loud enough? Great. So I'm going to tell you today about several experiments we do that take advantage of collective cavity QED physics to look at interesting collective phenomena. That's what we're interested in. We're interested in not having just individual atoms and single atom physics. We want to somehow build connections and links between the atoms. And so this is done at, here at JILA and Department of Physics at the University of Colorado. So just to restate that, we're trying to generate not just individual atoms and look at single particle physics, although we're happy to do that when it's interesting. But we're really interested in thinking about developing correlations and entanglement between atoms. So somehow they're linked to each other. They're not just doing their own independent thing, bouncing up and down here, but there's some kind of link between them. And the way we're going to do that is not by having them actually get together and talk to each other directly. They're actually going to interact in some way through an optical cavity. That's the idea. In order to do this, we're not going to focus on a particular tool of quantum mechanics. We're happy to use it all. So we're going to think about unitary dynamics, the quantum measurement process, and dissipation in some cases to do this. Okay, so there are actually three experimental systems. These are all laser-cooled systems. We laser-cool and trap rubidium, as well as strontium atoms. And there's one project in rubidium, two projects with strontium. There's actually where Matt Norcha, graduate student at the time on the strontium experiment, is standing. That's where the third experiment is now sitting, involving strontium atoms. If you come and visit the lab, you would see that there are three optical cavities with laser-cooled atoms inside of them. So for instance, here's a magneto-optical trap of rubidium atoms in between two mirrors. Here is strontium atoms, and there's a mirror here and a mirror here that we then load the atoms into that cavity. And then most recently, this is a ring cavity, and this sort of black spacer is there to avoid light scattering. So we coded it black, that's why it's hard to see. But there's actually a ring mode that runs kind of like I'm tracing out here in kind of a triangle. And that little sort of blue streak, that's actually strontium atoms inside of a 1D optical lattice inside that ring cavity, being loaded from a beam up above it. I'll just briefly touch on that experiment just a little bit. Okay, so where are we going? There are three different sort of broad topics I'm going to try and just give you an update on today. One is thinking about how to realize ultra-stable superradiant lasers. Another one is thinking about how to get unitary interactions between the atoms, spin exchange interactions, and the observation of a dynamical phase transition. And the last one, which is actually our newest stuff, is the observation of an entangled Matterwave interferometer. Okay, so let me break each of these down, just the high-level summary. So we're trying to break through thermal limits on laser frequency noise. If you want to build very, very stable frequency lasers, this actually turns out Brownian thermal motion associated with the laser can limit your frequency stability. So the goal here is we're going to build a type of laser where we hide the laser's phase information and collective state of the atoms. Apparently I've got timings on it. It keeps trying to advance on me. The goal here is 100 times reduction in laser line width for frequency, length, and maybe even gravity metrology compared to state of the art. That's the long-term goal. I'm also going to tell you about how we can work in a regime where we can generate spin exchange interactions mediated by the cavity between the atoms to generate sort of flip-flop interactions where you get correlated flippings of the spins. And this we use to create twists and energy gaps that might be useful for generating entanglement, stabilization against dephasing, and exploring non-equilibrium phase transitions. And lastly, I will tell you about phase sensing below the standard quantum limit. And the goal here is to create entanglement enhancements for quantum sensors. Okay, so let's return to this first topic, trying to break through quantum limits on laser frequency noise. The idea, like here's the idea. It was proposed in 2009 here at JILA, Meiser, Holland, Yi, Carlson, and then a similar idea was put forward in China in 2009 at the same time. Our version of it looks like, let's take strontium atoms that we build optical lattice clocks with here at JILA and Jun Yi's group, for instance. There's an excited state that has a lifetime of 118 seconds. That's a ridiculously long time. The reason for that is it's a triplet to singlet transition, and it's a J = 0 to J = 0 transition. So it's doubly forbidden. So it lives a really long time. So what would be reasonable to do that with that? Well, let's put lots of those atoms inside of an optical cavity and actually try and get that sort of collection of atoms that don't like to emit light. Let's actually try and use them as a gain medium for a laser. And the prediction was that you could be more than 10,000 times less sensitive to cavity frequency noise. The fact that the resonance frequency of the cavity that these atoms are inside of, because that changes as a function of time due to, say, thermal Brownian motion, that if you were to use these very narrow transitions, the lasing frequency would be really tagged to the atomic transition frequency. And so you might ask, yeah, that's cool, but what about more fundamental things like quantum limited line width? There's always some kind of shallow Towns line width for lasers. It turns out you can write that in terms of the single particle cooperativity times the single particle radiative lifetime, which here is a millihertz in terms of line width. So that says we could get sort of, shallow Towns line widths of millihertz. So this all seemed encouraging, okay? And so we actually explored this physics in rubidium using Raman transitions to mimic a narrow transition, and there were follow-up papers to this one. But it looked really encouraging. So we said, okay, let's move forward with this. So we're going to rely on a kind of regime of laser physics that involves sort of superradiance. And I want to give you sort of a very classical view of what superradiance is. Okay. So we all know Rabi flopping. So if I take a laser and I shine it on a collection of atoms, and let's imagine it T = 0, I turn that laser on and the atoms are all in one state, I will drive Rabi flopping between the ground and excited state. Okay. Okay, nothing new here. We describe that on a Bloch sphere in terms of there's some collective spin vector describing the atoms. When it's pointing up, it means all the atoms are in the excited state. When it's pointing down, all the atoms are in the ground state. But then the field that we're applying, we describe by a fictitious magnetic field, which is this red arrow over here. And we essentially generate a torque about that red arrow that actually causes the spins to precess. So superradiance, I kind of conceptually think of as a self-driven pi pulse. And the basic idea is that now the field that the atoms are going to see is actually the field that's radiated by the other atoms inside the cavity. And so what that means is if you think about, I've got some dipole moment associated with this collection of spins. This is an optical transition. It's the optical dipole moment. It radiates some electric field into the cavity. And then all the other atoms see that field that was radiated to the cavity. And so we can describe sort of this fictitious self-radiated field as something proportional to JY x hat plus JXY hat when you go through the math of the optical Bloch equations. Okay. And so that means that if at T = 0, I start in the excited state, essentially it interacts with its own field, and its own field drives the collective spin from the North Pole to the South Pole. But the cavity is highly damped. So by the time the atoms reach the South Pole, all the field has escaped and they come to equilibrium. They rest at the bottom. Okay. So it's kind of like it's just like a Robbie flop, okay, between excited and ground state, except it's its own field that generates this torque. So we built an experiment to do this. The first time it worked, this is really Superradiance on a very narrow transition, the millihertz line with transition in strontium, appeared in Science Advances. At t equals 0, we put all the atoms in the optically excited state, and then we wait and we look at the amount of power coming out. We detect the power coming out of the cavity as a function of time. If we put 200,000 atoms in the excited state, nothing happens, nothing happens, nothing happens, and then suddenly we get a burst of light. And then it decays. And this burst of light is exactly a superradiant pulse coming out of the system. Now, note here that the delay time is of order, 75, 100 milliseconds. The pulse width is of order 50 milliseconds, which means that this is a very strong stimulation process. Remember that these atoms like to only, single particle decay is 118 seconds, and this is 50 milliseconds. So it's a very strong stimulation process. We can look at the scaling of the time scale for the pulses coming out as we change the atom number from 200 to 150,000 to 125,000, et cetera. And we see this delay and spreading. You can also integrate up the number of photons inside this pulse, and it says that, for instance, 90% of the atoms are in the optically excited state, emit a photon into this collective pulse of light. So in addition to our work, just before this, we saw similar physics where we could go from sort of a superradiant regime or a bad cavity regime into the normal laser physics regime, where you think of the cavity as being actually sort of the holder of phase information on a 7.5 kilohertz transition, as well as doing some continuous optical repumping. But then more recently, for instance, in Andreas Himmert's group in 2019, they were able to look at for physics here, as well as look at the statistics of pulse delays and the quantum noise in that process. And then there's also work in Jan Thompson's group at the Niels Bohr Institute, Copenhagen, looking at the 7.5 kilohertz transition. Sorry, I said that wrong. It's the 375 hertz calcium transition where Andreas Himmerich saw that physics. Had that backwards. Both of these are, I believe, sorry. This one is actually Katori, if I've got that right. Was doing this, but in an optical fiber. This one is in a cavity at the Niels Bohr Institute. My apologies. Okay, so the idea is that we want to—
James?
Yes.
So just a quick question. Can you remind me what determines the delay in having the superradiant burst?
Yeah.
So I see that depends on the number of atoms. It should be standard Dickey superradiance, but I don't remember right now.
No, that's fine. So it turns out that the time scale is set by is sort of shortened by order n. So the time scale to reach the peak of this pulse goes like 1 over n gamma.
Right,
So
right. But the mechanism why you have a delay that depends on the number of atoms.
It's basically what is the characteristic time scale to sort of cascade down the Dickey ladder of states.
Mm-hmm.
And essentially you can kind of think of it as the bulk of the work is done near the peak.
Oh, sure, right? Sure. It's completely obvious.
The upper power goes like n squared C gamma.
Yeah. Now I see perfectly. You are descending the ladder of Dickey states from the one with maximal m that is proportional to m up to the one with m equal to 0. So of course the burst is when m is equal to 0, and so of course it's going to depend on that. No, sure. Thank you.
That's exactly right. So it goes faster. You can see the pulses arrive earlier as you increase the atom number, because it goes like 1 over C gamma.
Indeed, it was standard. Just I needed a refresh. Thanks.
Sure, absolutely. I will also comment that this is actually seeded by quantum noise, to the best of our understanding. We really are, there's no coherence between the ground and excited state for these pulses. So quantum noise is what kicks this off. It's spontaneous emission into the cavity mode that then ignites the fuse, and you get a runaway pulse of light. We wanted to build narrow line width lasers, use this as a frequency reference, or ultimately in the long run a phase reference. And so we explored that by comparing the frequency of the laser pulses coming out. We get about 1 pulse per second. We get 1 pulse, we throw the atoms away, we load new atoms, we do that about 1 hertz. And we can actually compare the frequency and heterodyne of those pulses of light to this Ferrari of reference cavities down the hall in June's lab. Okay, so this is a really highly engineered reference cavity to give us very, very ultra stable light to do heterodyne detection of the pulses of light against. And so we could treat it like a clock. You would just think of it as, we get some pulse of light and we ask what's the frequency of the pulse of light relative to this reference cavity as a function of the number of pulses that we average over. So you can look at a fractional Allen deviation. And so actually just concentrate on the black points here, the Allen deviation versus measurement time. And then if we optimize things, we can get down to here. So we get a fractional frequency stability for a single pulse of light, 1 per second, about 7 to 10 times 10 to minus 16. Half of that, the red points is a background measurement we made that allowed us to establish about half of that is from photon shot noise of the superradiant laser. We've got a pulse of light that lasts 50 milliseconds. So you get a Fourier transform broadening on that pulse. And then it's a question of how many photons do you get and can you collect to split that line? Okay, so about half of that is photon shot noise and about half the noise is actually coming from this Ferrari of reference cavities. So we were pretty happy about that because this is the first of its kind of object. And yet here's this highly engineered object. We're doing pretty well. So we're happy. You could also ask about relative accuracy of the light coming out, at least relative to one of Jun Yi's last clocks. And we can constrain that to be within about 4 times 10 to minus 15, but we didn't push hard on that.
Sorry, what were the 2 colors or 3 colors of the points?
Yeah, I'm going to give the highlight here, and so I apologize. I should just remove it if I'm not going to talk about it. The black is that actually what we're doing is we're actually optically pumping half the atoms into a nuclear spin state plus 9 halves, and the other half the atoms in each experiment into minus 9 halves. And then we generate a superradiant pulse on both of those. We have a magnetic field that allows us to distinguish the light emitted on those 2 transitions at the same time. And then so we get 2 peaks in the Fourier transform, okay, in the power spectrum. And so what we want is the average frequency of those 2 peaks. And the average frequency tells us sort of like what's the 0 magnetic field atomic transition frequency. So it's a kind of a way of getting rid of magnetic field noise. But on the other hand, our magnetic field is pretty quiet. And so we could say, well, but if we look at the difference frequency between these 2 pulses of light coming out on a single shot, we can ask how much of the noise is coming from photon shot noise, because all the optical phases drop out when you look at the difference frequency between those 2 pulses of light. And that's what the red points are. And that's how we can establish what's sort of our photon shot noise limit associated with sort of the pulse of light. That's where we're getting it from. The blue point is we did take a lot of data there, but we really optimized things. Sort of got there's all like kinds of like path-link stabilization you have to do, like phase, optical phase stabilization you have to do in order to really pull this out. So when we really optimize things, we can push it down to around 7 times 10 to minus 16. So one of the claims is that we'd be less sensitive to noise in the cavity resonance frequency. And so we can actually directly observe that. Here's kind of the cavity resonance frequency in blue, in a cartoon picture. The laser light comes out at some frequency in red, but then we can shift using piezos the cavity resonance frequency to some value and ask how much does the laser frequency change by? Because the idea is that mainly it's tied to the atomic transition frequency. So sure enough, we can change the cavity resonance frequency down here. This is in kilohertz. So from minus 25 kilohertz to plus 25 kilohertz, but the laser frequency changes by order -1 to +1 hertz. And so that says it's very, very insensitive to changes in the cavity resonance frequency. For a normal laser, this ratio of change in laser frequency to change in the applied cavity resonance frequency would be 1. And here it's about 2 times 10 to minus 6. So it says we can be highly immune to thermal and technical vibrations. Maybe these can be even deployable outside of science labs. Lots of technology development to be done, but okay, like the fundamental sensitivity looks encouraging. So it's encouraging enough that, if we're getting pulses of light, wouldn't it be great if in fact it was just a continuous laser? because then you can think of it as a phase reference, not as frequency reference. You just have a continuous phase that's evolving. In the long run, you just phase lock a laser to this reference. And so we've built up we're building up a CW system to try and get CW lasing, where we're loading atoms from a beam of strontium atoms up here. We then create a cold beam that comes down through a baffle for screening light. And then we're loading them into this ring cavity so that we can load them in this region where lots of perturbations to the lasing transition would happen. And then we've already observed that we can do transport of the atoms along the cavity axis into a region where there's no laser light, at least no intentional laser light, to hopefully laze down in this region. That's the long-term goal. And so the potential frequency stability you could imagine getting, if everything were to just scale, could be around 5 times 10 to minus 18 at 1 second. So general relativity gives you shifts of order. We can resolve a change in our sort of gravitational potential of a height of about 6 centimeters in 1 second. So you could imagine that you could use clocks to actually map out geo potentials. That would be one potential application. I will also mention that superradiance is one way to find the atomic transition frequency, but you could also just kind of think of it as, well, I just want to do what I normally do when I lock a laser to some vapor cell. I just send some light through and I look how the light is modified by being on resonance with an atomic transition frequency. And so we can actually do that. We can send probe light through our cavity. We can look at the transmitted field. If the cavity is empty, here's a theory plot, that here's the cavity line width, just a Lorentzian. And the idea is that if you have this very narrow transition, you'll see a very, very narrow absorption dip right in the middle. And so when we zoom in on this and we do the experiment, here's the detuning of the probe from the atomic transition frequency in kilohertz. And again, in this case, we have half the atoms and minus 9 halves, half the atoms and plus 9 halves. There's a magnetic field. So actually we see 2 atomic transition frequencies. So we're seeing a direct modification of this probe light, even though it's a millihertz line with transition. So we could take advantage of that, not for laser locking at the moment. We might come back to that at some point. But we are actually able to look at, say, the phase shifts induced on the probe light as a way of characterizing the strength of the interaction of the atoms with this cavity mode. By doing that for 2 different transitions at the same time, it allowed us to essentially avoid having to do a pitch drop experiment to measure the natural lifetime of this clocked state. It turns out it's really hard to just wait around for these atoms to decay to figure out what the natural radiative lifetime of this transition is. And so instead, we can actually do this kind of cavity QED trick that allows us to measure the ratio of interaction strength on 2 different transitions and pull out a line width over here. So we now know that radiative lifetime is about 118 seconds.
James, a quick question. Do you need then a probe that has a
Yes.
sub-millihertz line width, and do you have such a laser?
No. So the line width of this laser is sort of, I would say, sort of, it depends on how good of a job we're doing, but sort of hertz to 100 millihertz. The idea is that in the long run, what you want to do is you want to pre-stabilize a laser to an optical reference cavity. But then you essentially servo and take out the low frequency noise associated with that cavity by comparing the laser light to an atomic transition frequency that has really good, very low 1/f kind of noise. Does that make sense? So it's like any oscillator, basically you say in what frequency domain at some offset from carrier is a given oscillator better than another oscillator? And then you build a composite oscillator out of that.
So in the end, you in some sense do have a millihertz probe laser. Yeah.
The idea is once you close the loop, that maybe you could get down to sort of millihertz or 10 millihertz kind of sort of stability associated with your laser. That's right. But there is a very important thing here, which is if I start with a megahertz line with laser, in order to narrow that laser down, I need measurement bandwidth. So I can build a servo with a bandwidth that's more than a megahertz to bring that spectral power into a carrier, right? But because really the rate at which we can get information is relatively slow here, kilohertz bandwidth is more reasonable to think about for these servos. And so that means that you really need to already have most of your power well within that 1 kilohertz servo. So you need pre-stabilized lasers, but you don't need pre-stabilized lasers that are stabilized to 1 millihertz.
Thank you.
Mm-hmm. Okay, so now I'm going to switch gears. I'm going to still talk about strontium atoms in the optical cavity, but I'm going to describe this work where we could see spin exchange interactions mediated by the cavity, where essentially one atom is in the optically excited state, emits a photon into the cavity, another atom that was in the ground state absorbs it and flips to the excited state. That's the idea. How do we do this? It's really kind of dirt simple. We take our previous system. We had a cavity that we tuned onto resonance with the atomic transition frequency, and we described the superradiance as there was some collective vector here, block vector, and it radiated a field that created a fictitious magnetic field that would torque this vector from the excited state, would move on the circle to the ground state, and that generated light out of the cavity. Okay. Now let's actually tune that cavity mode off resonance from the atomic transition frequency. So now think of it as the atoms have some dipole moment. That dipole moment is radiating field into the cavity mode. Now previously that field was on resonance with the cavity mode. And that cavity mode is basically a harmonic oscillator. Now what happens if the cavity mode moves off resonance? Well, now I'm driving with this dipole field into this, trying to drive this harmonic oscillator, the cavity, but now I'm off resonance, way off resonance. And so as a result, I get a pi/2 phase shift in the steady state field that is established inside the cavity. Because when I drive a harmonic oscillator on resonance versus off resonance, there's a pi/2 phase shift in response. Okay. And so what that shows up in the fictitious magnetic field is that instead of the fictitious magnetic field being perpendicular to the projection of the block vector onto the equatorial plane, it actually picks up a pi/2 phase shift. So now it's actually underneath the block vector, or almost totally underneath it. And so that's going to drive different dynamics. It's not going to drive stimulation of atoms from the excited state to the ground state. It's actually going to drive a spin exchange interaction. So let's work through that just for a moment. So the claim is this pi/2 phase shift, when you tune off resonance, basically modifies this fictitious magnetic field describing the system. So now the fictitious magnetic field lies in the same orientation in the equatorial plane as the projection of the block vector. So B now looks like JXX hat plus JYY hat. It's proportional to that. So let's plug that into this J dot B Hamiltonian, and we get JX squared plus JY squared. Let's define these objects. They're classical objects so far, J plus minus, which are JX plus or minus IJY. If we substitute in, we get something that looks like J plus J minus. And now let's pretend we're doing quantum mechanics by putting hats on everything, and then we'll call these J plus J minus objects collective raising and lowering operators over here with some kind of coupling coefficient chi. In quantum mechanics, you would describe these in terms of individual polyspin matrices for each atom that you're summing over all n atoms over here, and these are the individual spin, flip-flop terms for the atoms, but it's an all-to-all interaction. Okay. So we can actually look at what are the dynamical consequences of this spin exchange interaction. And we can rewrite this J plus J minus if we only keep collective terms in terms of a total spin squared, so J squared, minus JZ squared term. And so there are dynamical consequences. Let's look at the JZ squared term. We expect that what this should give is one axis twisting and could be used for generating squeezed states or entangled states in the future. And so this would lead to a shearing of the block sphere that, the precession frequency depends on how far off the axis you are. The J squared term would lead to a many body gap protection, which says if I shorten my block vector, there's an energy cost associated with that. And so this could stabilize you against single particle dephasing. So we were able to experimentally see this one axis twisting dynamics on the millihertz line with transition. I'll tell you about that one. Here's some data where we vary the inversion, spin projection JZ at t equals 0. We can set it. And we look at the frequency of the laser light that comes out. And that's that frequency of the laser light, the small amount that dribbles out, because we're way off resonance. So there's still it's small, but a little bit dribbles out. We can look at the frequency of that light as a way of figuring out what the spin precession frequency is. So we can look at that, and we can see that as we vary that inversion from being near the south pole, almost all the atoms in the ground state to the atoms in the excited state, that we see this variation that is a linear variation in the spin projection JZ, like you predict from this Hamiltonian. We can also fix the inversion somewhere just above the South Pole, and we can vary the detuning from resonance. And we see that essentially we can actually flip the sign of this chi. Here's the predicted variation of chi with detuning of the cavity from resonance for the atomic transition frequency in units of the cavity line with kappa. And you get this dispersive curve, and sure enough, there it is. So with this, if we could improve this in the future, you could imagine that you could create spin squeezing with this. At the same time we were seeing this, there was a theory proposal for spin squeezing out of Vaughn's group. We have a proposal a little more complicated for creating two-mode squeezing using ensembles, but the squeezing is essentially generated at JY squared, kind of Hamiltonian. Okay, so we've used this.
Hey, James.
Yes.
Just one question. So talking about improvements in the near future, what about going in some sort of more many-body regime that is not collective? So somehow not having all spins talking to each other with the same strength, but talking with some, let's say, atom-dependent strength. So having some chi of I and J. I mean, we both know very well that Monica is doing it. I'm asking whether you can do it or whether you want to do it for reasons that will be clear in my talk tomorrow. If you come to the CMQ talk tomorrow, I will show you something in that direction. So it's clearly an interesting question, but please.
So I think that some of the directions we're interested in are thinking about disorder, where basically you add in disorder and ask what happens when you have the spin exchange interaction. That one's kind of a little more straightforward. We're interested maybe in exploring the fact that in strontium, because of the nuclear spin degree of freedom, it's a spin 9/2 nucleus, that you could have 20 different levels involved. So thinking of that as a synthetic degree of freedom in the system. It is possible that you could imagine engineering interactions between sub-ensembles. I think we've got enough stuff that probably that won't be our first thing to do, is to try and engineer arbitrary, chi ij kind of terms.
But just for my own education, what's the difference between your platform and the one of Monica, for instance, in terms of engineering spatial dependent interactions? Because I'm more talking not adding a disordered field, but having really the interaction that is that is independent. So as you said, interactions between ensembles, because from my, let's say, elementary eyes as a theoretician from the outside, I don't see immediately a huge difference. So
no. So in fact, what I would say is the mechanism I've described. Remember I said when we were doing superradiance, I mentioned that we said, let's build artificial optical transitions using Raman transitions. Basically that's the analogy here. Like, we're doing this on a true optical transition, but there are lots of groups around the world where you use Raman lasers to address, stable ground states of, say, rubidium or other alkali atoms in order to mimic very narrow line width transitions.
Right.
And so the one advantage that I would say Monica has is that she has the ability to, tune the atomic transition frequencies associated with those optical transitions to get this sort of like which spin clusters or which spatial sort of little groups of atoms are going to interact with which.
Yes.
Right. And so she has an extra degree of freedom there. On the other hand, I will say that one thing that can be a little bit complicated in these systems is unless you deal with inhomogeneous coupling to the cavity mode, that it gets a little bit tricky because you also end up inducing AC Stark shifts in your system that's associated with generating that you want this dress-like excited state, but at the same time you're off resonance from a true optical excited state and you've got AC Stark shifts to deal with. There's also the element of, in the long run, I like to see these connections between many body physics and precision measurement. And so doing this in strontium, we like the idea that, well, this is really kind of a leading platform for thinking about, quantum metrology and making measurements. So that side appeals to me a little bit.
Well, again, giving a teaser from my talk tomorrow, this would imply somehow seeing the advantage of squeezing for finite wave vector K, right? Because so far, I mean, in my experience on squeezing, all precision measurement is for collective modes. And these are, correct me if I'm wrong, enough for most precision applications, right? So having squeezing for finite K and not only for K equal to 0, I mean, do you know anything interesting you could do with that? Because there are very few papers around.
Well, when you say for K equals 0, what I would say
Collective
is,
magnetization and
I
then squeezing
understand.
forever if we.
But in reality, if you go into the lab frame, we're never building spin waves with K equals 0. In
Yeah,
reality,
sure, because
these atoms are
absolutely.
distributed along a cavity axis. If we were
Sure.
doing this in a ring cavity. So we're really never doing it in a K equals 0. In fact, it's always at some finite e to the ik with
Okay.
K non-zero.
Okay.
But on the other hand, like there is a question of, more complicated systems where, for instance, if I want to make a differential measurement between two ensembles, that like two-mode squeezing, for instance, right?
Right.
Yeah. So for sure, that kind of stuff would be, for certain applications, could be really, really powerful.
Okay. Okay. Maybe we can rediscuss more tomorrow, please.
Sounds great. Sounds great. So in the next topic, we were trying to take these spin exchange interactions and apply them in the context of thinking about a kind of dynamical phase transition. Okay, and so that work was here in 2020. And the idea is that there's some phase diagram and we'd like to see if we can explore it. Okay, what is this phase diagram? Well, first off, there are all kinds of phenomena that people are thinking about now in many body systems. It's kind of new phenomena of equilibrium, non-equilibrium phase transitions in open quantum systems. There's beautiful work being done all around the world, at ETH and Stanford and Hamburg and Tübingen and MIT and Berkeley and all these places where the dissipation is very important to the dynamics. And so that's being done in cavities with cold atoms, for instance. What I'm going to tell you about is a dynamical phase transition in terms of the relevancy of the dynamics. It's essentially in a closed quantum system. And the idea here is to actually see an abrupt change in the dynamical behavior is characterized by some time averaged order parameter. Okay, that's going to be a working definition of what we're going to look for here. There are other experiments that have seen this in ion traps, in cold atoms in Hamburg, in RF ion traps at JQI, and in cold atoms in Toronto. There are different ways of talking about this. Sometimes people refer to something called a Low-Schmidt echo as a way of characterizing a dynamical phase transition. But here we're going to look at this sort of change in dynamical behavior I will tell you about, and that's more close to these experiments over here at JQI and in Toronto. Here's the Hamiltonian we want to build. Here's what's going to be involved in the phase transition. We want a spin exchange interaction. I just showed you we have that. We want a sort of a longitudinal field, which we can get by actually just detuning the cavity from resonance with the atomic transition. Here I called it, let's see, sorry, this is detuning a dry field from resonance with the atomic transition. That's a little delta here. Here's an atomic transition frequency. Here we're going to go to a 7.5 kilohertz line with transition in strontium. It's very narrow. And then we're going to detune by a few megahertz or 0, but that's about the range. And then we're going to have a Rabi frequency that we associate with this input field that actually can act as a transverse field that can drive Rabi flopping over here. This is all in a very far detuned limit. So the cavity is actually sitting over here detuned by about 50 megahertz, and it has a line width of about 140 kilohertz. Okay. So we get this spin exchange interaction, and the characteristic energy scale associated with that is about half a megahertz at this detune for about 100,000 atoms. So it was predicted that if you have this phase diagram, let's go to the delta equals 0 case. So the field that we're going to inject into the cavity is on resonance with the atomic transition. That's what it means. So now we're going to have spin exchange plus a transverse field that wants to drive Rabi flopping. The idea is that at delta equals 0, the phase diagram looks like this, that there's a ferromagnetic phase where if we begin with all the atoms in the ground state, all the atoms will like to stay in the ground state. But as we increase the Rabi frequency relative to chi-n, the energy scale of the spin exchange, eventually it'll start Rabi flopping, and in time average, it looks like there's 0 net spin projection. And that's what's meant by time average. So let's look at one data point here. So it's a quench experiment. At t equals 0, we begin with all the atoms in the ground state. We're in the limit where the spin exchange interaction is dominant over the Rabi flopping over here. And so the atoms actually kind of get stuck near the South Pole. They just can't get off the South Pole. Now, if we actually do the same experiment But now we move up in our Rabi frequency. So we begin in the ground state, and then we turn on the magnetic field. I'm sorry, the magnetic field, the Rabi frequency, the transverse field, by injecting the light into the cavity. Then we begin to tries to Rabi flop, but it can't quite get off the south pole. And as we go up and up in that Rabi frequency, eventually it breaks loose, spin exchange doesn't matter anymore, and it just Rabi flops. Okay, so now I've got Rabi flopping and time average, there's no net magnetization. So we can actually look at the spin projection JZ over a small time window at some time offset from 0 after the quench. We can actually plot that for different atom numbers as we vary omega relative to chi-n, and here's the time average spin projection JZ. And so we can do this for different atom numbers. This in millions of atom numbers. We get these curves. If we renormalize in terms of chi-n, these curves collapse on top of each other. This end of the phase diagram is where the spin exchange interactions are the dominant energy scale. This end of the phase diagram is where the transverse field is the dominant energy scale, essentially Rabi flopping, single particle Rabi flopping. And there's a transition in between in terms of the dynamical behavior of which one is dominant. What do we see? We can also explore this phase diagram horizontally, where we change the detuning from resonance while holding the Rabi frequency fixed. So we change this delta. And so we can, for instance, work at positive and negative spin exchange interactions. We could scan the detuning and then do our quench and look at sort of the time average magnetization after some time delay. And we see that actually, here's what you would expect for just single particle Rabi flopping. And we see that actually we get these frequency shifts, these kind of nonlinear responses in the system. We can also explore along this dash curve further up the diagram, where the Rabi frequency is larger. The gray is again what you would expect for single particle Rabi flopping. Let's just pick the blue points here. We see that we get this sort of modification of the line due to this nonlinearity introduced by the spin exchange interactions. So with that, we were able to explore this 2D phase diagram. And there's something I won't tell you about. We could also play around with the initial state. So look at what how the phase diagram is modified. When we don't begin at t=0 in the ground state, we actually can arbitrarily prepare points on the block sphere and see what happens to the dynamical phase transition. So in the future, we're interested in the interplay with disorder. What happens when you include dissipation? Can you move beyond 2 levels? Can you maybe even generate entangled states? We also have some interest in simulating a BCS Hamiltonian. There's a theory proposal down here I'll reference you to, as well as exploring some emergent dark states in this multi-level system when you take advantage of the fact that you've actually got 20 levels that you can drive. And you can find sort of these potentials where you relax effectively into these dark states in a long time. Okay, so the last topic I'm going to talk about today is the generation of an entangled light pulse Matterwave interferometer. This is on the archive, came out, I think we posted it in October. So this is a really hard experiment. Graham Greevy and Jingyi Liu are really the 2 authors on this paper that made it happen. And so I really want to highlight them. They both equally contributed to this work, and I really like this work. Okay, so if I have 2 canonically conjugate variables, there's some uncertainty relationship between them. The Heisenberg uncertainty relationships that we can think of it as there's kind of a classical part of some, describing where you are in phase space, but then quantum mechanics sets some uncertainty blob, some uncertainty in your ability to know exactly where you are in this phase space. And that's bound to be bigger than 1/2 h bar. For angular momentum components associated with spin, you also have commutation relationships, and that actually sets an equivalent Heisenberg uncertainty relationship on spin projections, which we can recast as uncertainty relationships on the angular orientation of a collective block vector. Okay, so the product of the uncertainties and the polar angle times the azimuthal angle has to be greater than or equal to 1/n, where n is the number of atoms that block vector is composed of. And so if you set these equal to each other, which is what you have when you have an unentangled state, this gives you an uncertainty of 1/√n radians. So this uncertainty, it turns out that almost every precision measurement, not all, but a pretty good class of them, get mapped onto essentially this kind of block sphere picture. And the goal of the experimentalist is to say, at the end, I need to read out my precision measurement and ask, where is this block vector pointing? And this uncertainty sets a limit on your ability to make that measurement very precise. And so there's the idea that you can actually entangle the atoms with each other to actually do better. And there are two different broad classes of ways that entanglement can help. One is that in the end, what it allows to happen is the atoms can conspire together. They know about each other. You're not running n-independent experiments anymore. They can conspire so they either work together to partially cancel each other's quantum noise. So for instance, we can build a sharper clock hand here. And if I was building a clock or a Matterwave interferometer, I could tell sort of where my meter is pointing better. The other way is, for instance, with GHZ style states, where you increase the rate of phase accumulation. But in either case, you're using the entanglement to somehow enhance your precision. So people have been working to build entanglement between atoms and ions. And so there are many ways to do this, but I'm just going to highlight 4 of them. One is based on ions. This was some of the earliest work where you use the motional common mode, motional degrees of freedom shared between ions to create entanglement between them. Here are some references. The other way is to have very cold atoms, BECs, degenerate gases, where the atoms actually collide with each other. And you get some kind of interaction energy associated with those collisions that can generate entanglement. Another way to do it is not to let them collide, but rely on sort of dipole-dipole interactions, Rydberg-mediated style interactions between atoms. And so, for instance, people have built GHZ states associated with that. What I'm going to concentrate on here are light matter interactions, where somehow you let atoms interact with a light field and you can generate entanglement. And there are 2 different approaches there that I'll explain. So here's my best summary that I know of what have we actually observed in terms of direct observations of improvements over the standard quantum limit. How is our phase resolution relative to the standard quantum limit improved? So this is on a log scale on the vertical, on the horizontal is time in years. And so, and this is in noise variance, okay, over the standard quantum limit. So 1 means essentially you have the same phase resolution without any entanglement. And so some of the early experiments were really done in sort of the Weinling group up the road and Didi Liebfried and Chris Monroe at the time, where they were entangling a few ions with each other. And then this was scaled to sort of order 5 to 10 ions in, for instance, Rainer Blatt's experiments as well. That's sort of the ion trap approaches. People figured out how to let atoms bump into each other and create entanglement. And so that's the sort of vertical diamonds here. And so, some of the earliest work, Marcus Oberthaler's group and Georg Schmiedmeyer's group and Mike Chapman's group, Philip Troutline's group, and Carson Klem's group. Okay, there's some of the groups out there that have done that approach. For Rydberg atoms, actually, for instance, the sort of order 20 atoms in a GHZ-like state, Misha Lukin and Von Vuletich and Marcus Greiner are sitting here. I will also point out squeezed light, just to put squeezed light, what's the best you can do? Roman Schnabel keeps setting records on this. So, Roman Schnabel with squeezed light is sitting here and more recently here. The dark points are light matter interaction approaches. And so, Eugene Polzik was a pioneer in this, thinking in free space, and then experiments involving optical cavities and Von Voltage's group here and here, Morgan Mitchell's group, and then our group is in the red points here. So we're sitting here, and then Mark Kacevich's group at the moment. We're sitting up at about 18 dB of directly observed improvement over the standard quantum limit. Okay, so the 2 references for those are here. Jakob Reichel has also done this now using light matter interactions. People have taken these states and run microwave clocks below the standard quantum limit, built magnetometers that operate below the standard quantum limit, and some double well trapped interferometers, Matterwave interferometers, but in a trapped geometry. What I'm going to focus on now are actually these 3 points where, we were going up and up and up in my group in the amount of entanglement. Now we're going to drop down to here, but these are going to be interesting. I'm going to claim. Let me tell you about those. So it's our group and Karsten Klem's group. So those points are associated with trying to build a light pulse Matterwave interferometer. So just to remind you, Mark Kasevich and Steve Chu in '91, they demonstrated that you can use pulses of light to spatially split atomic wave functions and then allow them to sort of move apart and then bring them back and re-interfere them. And the idea is that you're giving pulses, momentum kicks to the atoms that drive the separation, and then reverse the separation to allow you to observe interference. So all kinds of applications for navigation, gyroscopes, accelerometers, gravimetry, fine structure constant measurements, testing QED by comparison to G factors of the electron, test atomic charge neutrality, dark matter searches for dark energy, geodesy, resource exploration, things associated with equivalence principle tests, measuring gravitational constant big G, and proposals in the future for doing gravitational wave detection in space. I'll just highlight that there are various proposals out there for doing this with Matterwave interferometers and optical last clocks, and we wrote a paper trying to think about what is the role of the atoms in these objects, because it was a little unclear to us. However, so far there's been no entangled light pulse Matterwave interferometer. There have been proposals for Bragg light pulse interferometers from Nicola Poli, Tino, and Vuletich here, and then also from Murray Holland and Nicola Poli here, and Andreas Shankar thinking about one-axis twisting using light matter interactions. Recently, Karsi Klipp's group was able to use collisional interactions to entangle spin degrees of freedom between atoms, and then use Raman pulses to map that entanglement onto momentum degrees of freedom. And they could see that they could do that mapping and get entanglement, but then they couldn't actually run, or at least they didn't demonstrate in that paper, an entangled Matterwave interferometer. They couldn't take that sort of entanglement that's generated in the momentum states and actually inject it into an interferometer. Okay, but the reference here, it's beautiful work. That was in collaboration with Ernst Strausel. Okay, so we're going to do that. We're going to try and build an entangled light pulse Matterwave interferometer that combines both quantum delocalization of each atom. It becomes delocalized in space due to being in different momentum states, but while also having entanglement of that degree of freedom between many atoms in our system. We do this in a cavity with a free spectral range of about 6.8 gigahertz, single particle cooperativity about 0.5, finesse of 130,000, length is about 2.2 centimeters. The mode waste is about 72 microns. The cavity line width is 51 kilohertz. This is in rubidium. We're going to work ultimately with about 1,000 atoms. The collective cooperativity, which is very important in these experiments, is about 500. And we're pretty cold. We're at about 0.7 microkelvin in the radial. It's not a BC though. And that gives us a thermal radius of about 3 microns, which is much less than the waste. So you can really should think of all the atoms as being tightly confined on axis with the cavity mode. Lasers everywhere. I'm not going to go into a lot of detail here, but I want to emphasize that most of our work is done by injecting lasers into different modes of the cavity at different wavelengths and different frequencies. So there are lots of lasers going towards the cavity in this experiment. I'm going to use this as a roadmap, but don't try and understand it. The idea is that, for instance, we can generate light into one longitudinal mode of the cavity, a TM00 mode, that establishes an intercavity lattice that we use for initially trapping the atoms in the cavity, doing lambda enhanced gray molasses and degenerate Raman sideband cooling to bring the transverse temperature down. We ultimately, for the interferometer, we switch off that standing wave light and we actually inject into the cavity a blue donut guide mode I'll talk about, which provides transverse guiding of the atoms as they fall under gravity. The idea is that to run this light pulse Matterwave interferometer, we need to give momentum kicks to the atoms. They need to be able to move along the cavity axis freely, but we don't want them to expand out radially. So we have some tricks involving injecting light into multiple longitudinal modes to build an optical dipole trap-like potential. That's in this paper here, but it wasn't done with the donut mode. So now we can realize this donut mode where we provide this repulsive potential so that the atoms stay right on axis. That's the idea. So I've told you about some of the ways we trap the atoms. I want to now tell you about how we actually give momentum kicks along the cavity axis. And to do this, we need to inject Raman laser light into the cavity. This is at about 80 gigahertz detuning from resonance with the atomic transition frequency. So we're going to send Raman tones towards the cavity that drive 2 photon Raman transitions with some controllable detuning from spin up to spin down. So this splitting here is about 6.834 gigahertz in rubidium. We're about 80 megahertz detuned from the intermediate states for this 2 photon Raman transition. In order to do this, we're driving TM00 modes, but we create sidebands off of a single laser using a fiber modulator to generate a tone that's 23 megahertz detuned to one side here and 23 megahertz detuned to the other side here. This is to avoid strong FM to AM conversion when you send this laser into this high finesse cavity. It's also that we're going to have to chirp the relative frequency difference between these lasers to stay on resonance because the atoms actually accelerate. So the Doppler shifts are changing as the atoms are falling. So being off resonance is good. So we can actually drive 2-photon Raman transitions where we change this 2-photon detuning. That's what's on the horizontal in kilohertz here. And if we let the atoms fall for a certain amount of time and we flip spins in a way that depends on the Doppler shift seen by the atoms, we can see that for certain detunings, there are lots of atoms that have a certain Doppler shift. That's the blue distribution. If we do shorter fall times, the atoms haven't accelerated as much and the distribution is down here. So we can wait some amount of time letting the atoms fall, they accelerate under gravity, and then we can actually drive 2-photon transitions with a very small Rabi frequency to do momentum selection. We can select a very narrow momentum distribution here with an RMS distribution of about 0.1 h bar k, about 800 atoms. That's how we get our atoms. Now I want to show you we can do quantized momentum kicks. The idea is that we can use these 2-photon transitions to both flip the spin and change the momentum state associated with the atoms. So if we begin with all the atoms, this is in a co-falling frame with the atoms, we'll call that 0 h bar k, that we can essentially turn on this 2-photon coupling and, for instance, apply it twice to drive a pi pulse first to this state and then a pi pulse down to this state. And then we can actually look at the velocity distribution like we did before. And so we see one peak associated with the 0 h bar k and one associated with the 4 h bar k. So we can give these quantized momentum kicks. We call these Raman in the sense that we're changing the spin state. That's what we mean here. So if I say Raman, I mean changing the spin state as well as the momentum state. There's something which is Bragg, which is also a Raman transition, but it's a Raman transition that doesn't involve flipping the spin. You just change the momentum of the atoms. That's what's meant by Bragg here. We can essentially do a series of pulses to actually derive to very large momentum. So for instance, we can first do 1 pi pulse, and then 2 pi pulses, and 3 pi pulses, 4, 5, etc. And so we can drive to very large momentum transfer of 10 h bar k in this case. So we can do all this with these kicks going in along this high finesse cavity axis. So I've told you about some trapping stuff, some transverse guiding, how we provide do the quantized momentum kicks. I'm going to tell you about how we generate entanglement in our system. Here's the key physics. There is a state-dependent cavity frequency shift. Okay, so we have atoms that are in state 2 h bar k spin up, and if we have atoms in that state, we tune a cavity to be close to resonance with this atomic transition frequency from up to some excited state E at 780 nanometers. Okay. So on a frequency diagram, here's the atomic transition frequency, here's the cavity resonance frequency. If I put atoms in this upper state, those atoms are close to resonance and they shift the atomic transition frequency. Okay. And because of that shift, that we can describe that shift as a QED Hamiltonian, where it says that it looks like, the number of atoms in spin up times the number of atoms in the cavity. But if you look at this, I could regroup this high QED and up term and think of this as a frequency shift to the cavity mode. Okay. So this is what's called a quantum non-demolition Hamiltonian. What it allows us to do is say that every atom that's in spin up or in this 2 h bar k spin up state looks like a piece of glass with some index of refraction that changes the round trip optical path length between the mirrors and shifts the cavity resonance frequency. But we can't tell which atoms are in 2 h bar k spin up. And so measuring the shift of the cavity resonance frequency allows us to measure NF without figuring out which atoms are in spin up. And that's the key physics here. It's a collective measurement. So here's how we actually do that. We actually detect, we send probe light at the cavity and we measure the Q quadrature, the reflected light, using a homodyne detector. So we get a dispersive kind of resonance. Here's with no atoms in the spin up state. Here's the dispersion, dispersive curve. If we put atoms in the spin up state, we see this shift. And so we want to measure this frequency shift very precisely. Okay. So that's what our signal looks like. if we do this twice, we can do a measurement of the number of atoms that spin up, and then we can apply a pi pulse to flip the populations, and we can measure again. So now we're measuring the spin projection JZ. And so by actually making this measurement very precise, even if initially there was some quantum uncertainty in where this block vector was oriented on this block sphere, which is now a combination of spin and momentum state at the North Pole and South Pole, we can actually localize the state to better than the original unentangled state. That's how we generate our squeeze states via this QED measurement. So we can actually look at the spectroscopic enhancement. It's basically how much additional phase resolution do we have. The standard quantum limit for unentangled atoms is sitting here. We increase our measurement sensitivity by sending more and more probe photons at the cavity to measure this frequency shift with better and better signal to noise. When we optimize things, we see that we can generate a directly observed squeezing below the standard quantum limit in this momentum degree of freedom between the atoms, 3.4 dB below the standard quantum limit. We can also generate a spin-spin dynamical momentum entanglement. This is following really kind of the approach that was pioneered in Vaughn's lab. And really it's the same physics, except now the idea is that because if we take a probe tone and we tune it off resonance with the cavity, the cavity resonance frequency depends on the spin projection JZ, and from shot to shot that varies. But the amount of light that makes it into the cavity now, because if the cavity is sometimes closer to resonance frequency and sometimes further away, it says that the amount that makes it into the cavity actually depends on the spin projection JZ. So if we take our previous QED Hamiltonian, but now we say C dagger C actually depends on JZ. That allows us to create a one-axis twisting Hamiltonian that looks like chi JZ squared. So we can actually apply this probe light for a certain amount of time. It creates this one-axis twisting physics I had mentioned before that drives shearing and creates a squeeze state, but it's a squeeze state at some small angle alpha. So we actually have to do a small rotation of order like 10 milliradians in order to 100 milliradians to bring that squeezing into the population basis. So that's what we're looking at here. And we actually see we drop below the standard quantum limit. When we optimize things, it's about 2.5 dB of directly observed entanglement below the standard quantum limit in this momentum basis. So that says we've got this quantum delocalization, we've got the entanglement between the atoms. Can we run an interferometer? And so what I've been telling you about is a sequence where in this interferometer, we're giving these momentum kicks so that the atoms spatially separate from each other and then recombine. And I've been telling you about this stage where we generate the entanglement. And so I've told you that we can actually generate these entangled states at this point in this diagram. And now the idea is we apply a pi/2 pulse that's oriented along the block vector to rotate the squeeze quadrature, the squeeze degree of freedom, into the azimuthal degree of freedom, which will evolve phase in the interferometer. So this really starts the interferometer. And now they traverse these two different paths. We do a pi pulse in the middle to reverse their momentums, to get them to re-overlap. And then we do a final pi/2 pulse that maps the phase that was accumulated in the interferometer back into the population basis. But that now also transfers the squeezed quadrature or spin projection into the population basis as well. And then we use our QED technique to measure the number of atoms that spin up or spin down. So we can run this sequence and we can actually look at it as a function of evolution time, the spectroscopic enhancement that we directly observe at the output of the interferometer, and we can sure enough operate this below the standard quantum limit. So it's about 1.7 dB below the standard quantum limit. The red points, we see that after a few hundred microseconds, we begin to lose operation below the standard quantum limit. But if we instead leave the squeezing in the population basis during the phase accumulation stage, we see that actually the squeezing is maintained. So what we believe is happening is there's technical noise that appears at longer times that's causing the azimuthal phase to actually get smeared out here. Okay, but the squeezing itself, we believe, survives. And so when we explore this, we think what's actually limiting this is just second order Zeeman shifts. That there's magnetic field noise in the lab, and we were operating a pretty big magnetic field to help resolve our states. So we think that this is something that can be solved in the future. So future directions for this are going to be thinking about composite sequences involving microwave and Raman transition and Bragg pulses. And in our early work, we were able to see squeezing where we weren't using an optical cycling transition. We could get a few dB, but ultimately we were able to get up to about 18 dB of squeezing. It was really because we could go to squeezing using optical cycling transition. So we're interested in if we can use these techniques to allow us to access an optical cycling transition. We're interested in Matterwave interferometry and trap geometries, thinking about manipulating von Near-Stark states, block oscillations, site-selective loading of atoms, and maybe even a scheme for continuous phase tracking that was put out by Athrea and Murray Holland's group that we collaborated on. So with that, I'm going to end. Thank you for your attention. I told you about how we're exploiting many atoms to try and do interesting physics, thinking about collective interactions. But I didn't do this work. Lots of really talented people did. And we have lots of wonderful collaborations throughout JILA with theory groups and other experimental groups. For the squeezing work, I'd really highlight Graham Greevy and Cheng-Yi Lo, Vera Schaffer, and Zhijin are sort of driving this continuous loading. Julia Klein really built that experiment up and has gotten the first results. And Dylan Young is the current student driving this kind of quantum simulation experiment was trying. So with that, thank you for your time.
Thanks a lot for this super interesting talk. Yeah, there were a couple of questions already in between. I'm sure there are more questions. I'm very happy that Bill Phillips also turned up as predicted. I mean, we now have statistical evidence that he always turns up if someone gives a talk from JILA, which is super nice. But also Morgan Mitchell and Andreas Hemrich turned up, so this justifies me leaving them on the email address. On the email chain, which I of course feel a bit guilty about. So, yeah, are there more questions?
Well, with that kind of a provocation, how can I not? But no, if Dima has a question, go ahead, please, Dima.
Well, okay. Actually, I have a non-physics question and probably a very hard physics question. So first of all, thanks so much, James, for a great talk, very interesting. My non-physics question is, I understand that Matt Norsha has graduated. What is his trajectory since graduation?
Yeah, so he went in, Matt was really fantastic. He built up that pulsed experiment, got tons of results out of it. He went and went to Innsbruck and worked on some of this sort of super solid stuff. And now he's actually back here in Boulder and he's joined a quantum computing company. In fact, I don't know what everyone else's experience is, but I think there are a lot of students and postdocs that are currently looking at quantum computing companies going, that doesn't look so unattractive. So he's back here in Boulder working with atom computing, thinking about Rydberg gates.
Right.
Sorry. In between there, I skipped over the fact that he worked with Adam Kaufman right here at JILA and did a short postdoc with Adam and got that experiment off the ground where they were able to see a tweezer clock as well.
So may I ask my hard question?
Yes.
We actually discussed this with you, I guess, each time we see each other at yes. So this Superradiant scheme is just beautiful. This is such a fantastic way to get narrow light. This is amazing. But my question is this: just fundamentally, if I have a narrow transition, so one way to interrogate it is to get basically this laser going, or a maser if it is in the microwave domain. And the other way is, like you said, using the probe spectroscopy. And if we put aside for a minute that it's hard to make a millihertz probe. Let's say it's a hertz width transition whose energy we need to determine, and you do have such lasers, right, at JILA. So what would be the fundamental limits in these two cases? Are they the same, or is there still an advantage of the superradiant technique?
Yeah, so there are two different types of superradiants I want to talk about. I'm going to pretend as though I have a CW superradiant laser for the moment, and I don't. But let's compare it to sort of like you would like a CW maser, right? One, you're not beating the standard quantum limit. Let me just say this like right up. Like what is the fundamental physics here? So sometimes people say, oh, there's magic, and it is kind of magic at first. When you say that I can have single particle broadening that is, 10 hertz or 100 hertz, and yet nevertheless the laser light can be much narrower than that. And so you say somehow I've gotten rid of single particle broadening, right? But you look, don't let anyone fool you. At the end of the day, all we have are Rabi frequencies and detunings, right? That's all this is, right? And so what's really happening is the self-radiated field inside the cavity, if you were to look at the Rabi frequency that's associated with that field, it's actually become larger than the inhomogeneous broadening of the ensemble. And so that says whether I'm exactly at the atomic transition frequency, or if I've been smeared off of, because of like some magnetic field or whatever else, Doppler broadening, I'm not at sort of the ideal transition frequency. Nevertheless, I'm within the bandwidth of the Rabi frequency, so I'll Rabi flop, right? I'll be driven from the excited state to the ground state. Okay. But if you think about what's the requirement to be CW, it's that you need to repump the atoms continuously, so when they hit the ground state, they go back to the excited state. Okay. Now let's imagine that you don't perfectly hit the south pole because you're an atom that compared to the rest of the ensemble is a little bit off resonance compared to the average. Then on the Bloch sphere, all you do is you create a circle that doesn't quite touch the south pole, right? And so you would get some kind of spreading and sort of the individual Bloch vectors describing each atom. But here's the magic. I repump, and the repumping takes out entropy because it scatters the field into free space, and deterministically, I always land back at the North Pole, right? And so what it says is, even if I'm off resonance, I begin to sort of spread out. The individual Bloch vectors spread in their azimuthal phases because of their detuning. It's okay because at some point they'll get reset to the North Pole and they'll start emitting again. So really the magic here is that it's that you're repumping at a high enough rate to erase the inhomogeneous broadening, that it doesn't accumulate as a function of time. So you're always destroying the phase accumulated by each atom due to the inhomogeneous broadening. So if you wanted to make an analogy, it's equivalent to saying that you're running repeated experiments of Ramsey experiments where the evolution time is of order 1 over the repumping time. And if you just think about it, who cares if I have a Doppler broadening of 10 hertz? If I make my Ramsey time 0.01 seconds, who cares if I have that broadening, because I'm just going to reset my Ramsey experiment. So I think there's a well-defined fundamental link. You're not surpassing any standard quantum limit. It's all Rabi flopping and detunings. There's an erasure of entropy from the system associated with the repumping, which is key. But you should think of the repumping time scale from the ground state to the excited state as the equivalent of setting the Ramsey time. Does that help? Does that connect?
I think that's correct. I think that's great. So people say that, well, let's look at the standard quantum limit, and there's somewhere a gamma, and if I do, let's say, a CW laser, that gamma could be very small. It's a Towns-Charlotte limit instead of, say, natural line widths, and so they say, oh, I win, gazillion orders of magnitude, and that's false, I believe.
I think that if I had to say, I would say that what you're getting compared to Ramsey, like why don't you just do this with Ramsey, is that if you can make this CW, then you get a phase reference. Whereas often what's happening with Ramsey is you're making a frequency reference because of the dead time in between the Ramsey experiments. And so by making a CW, you can really go to a phase locked regime, where now you have a phase reference. But of course, because of the shallow towns, you get a phase diffusion at long time scales that you have to account for. But I'm very suspicious that, I would love to do this paper, that if you were to compare, like, what's the phase diffusion you get from just repeated very fast Ramsey, that in the end, I bet it just ends up being the same as shallow towns. Yeah, there's just no new physics here, like between the two. It's just, it's a question of technology and what works well in a given configuration.
Thank you so much.
Are there more questions or comments?
Sure. Maybe I should show myself. Okay, anyway. So you mentioned that this is like a maser. So what I want to do is to explore how much it's like a maser. One of the things that if you've got an active maser, let's say you're talking about a hydrogen maser as a frequency standard, one of the things that happens with that is that at least for short times, the Allen variance goes down linearly with time when you're in this oscillating regime, as opposed to the usual thing with Allen variances that go down like the square root of time. Is that going to be true here as well?
So I expect it to, until you hit the shallow towns noise contribution. So here's my sort of my explanation of what Bill just said, and then Bill, you sort of riff on this if you like this explanation. And Bill, I'm looking at you, even though I know I'm looking away from the camera.
Sure.
Here's the idea that imagine our pulse superradiant laser. We get a pulse that lasts 50 milliseconds. So I've got Fourier transform broadening on that pulse, right? And then I also can split the line by the number of photons that I collect, right? So now let's imagine I could keep the same peak output power, but now instead of only lasting 50 milliseconds, I could go to 1 second. Well, that means it's lasting 20 times longer, which means my Fourier transform line width has gone down by 20.
Right.
And I've collected 20 times more photons. So my ability to split that line is also better. So in fact, you get a scaling with Allen variance that ends up going like, averaging time to the 3/2.
Okay, now I'm not quite sure I understand about getting more photons, because I thought that what you said was you were spreading the pulse out.
No, I'm gonna say that I build a system where I take that single pulse where I took the atoms from the excited state to the ground state and got 1 photon. But now I'm going to continuously return them to the excited state, and up to some numerical factor, which is going to be real in the experiment, I'm going to pretend as though I can do that repumping process with the same peak output power that I had in the superradiant pulse.
Okay.
Won't be true, but there will be a numerical factor on it. Okay.
Yeah, okay.
But my claim is that there are 2 scaling factors. As you increase the averaging time in a CW system. One comes from, well, your Fourier transform line width goes down, like 1/T, and you collect more photons, so your ability to split that line gets better. So you actually get a T to the minus 3/2.
Yeah.
I think that's what you're talking about.
Okay, except that my recollection is that in the maser, it was just T rather than T. It was just 1/T, T to the minus 1 instead of T to the minus.
Yeah, I don't want to speak for the maser community on that, but if I just do good old, like, what's the physics here?
I understand.
I get sort of if I could take my superradiant pulse with the same output power and I could just make it last longer, what would I observe? That's the scaling I predict.
Yeah. Whereas I think that what I'm talking about is actually running it so that it's lasing or masing, so it's continuous. And
no, that's what I'm talking about too. Like I'm trying to smoothly morph from how do I map the precision I had in the pulse system to if I could make that pulse system with the same output power, but last longer.
Okay, so I'm not sure, but I'll just have to see if I can figure this out. Why there's a difference between T and T to the 3/2, but because I'm pretty sure that the maser thing, but I don't remember the details of why. But anyway, that brings up another question. One of the things that is less well known about masers is the cavity pulling. Well, everybody knows about cavity pulling who works with masers. You're going to have cavity pulling as well. And the thing that I wanted to ask about is that in an oscillating maser, you have this cavity pulling term, which they get rid of by using a trick having to do with spin exchange. And maybe there's a similar trick here, but anyway, if the cavity is not tuned to the atomic resonance, then the cavity pulls the oscillating frequency a little bit.
Yep.
And that's an accuracy issue, not so much a noise issue. And the amount by which it's pulled is something like the amount of detuning times the ratio of the Q of the cavity to the Q of the atoms.
Yep.
Now, if it doesn't maze, and in fact, if it's very much below mazing, so that it's sort of like a passive filter, then it's the square of that ratio of the two Qs. And as you put more and more atoms into the mazer so that you get closer and closer to mazing, in other words, basically getting more and more superradiant effect, it goes smoothly from being the square of those two Qs to being the ratio of the two Qs. Not sure. I'm wondering if you're expecting something like that here as well.
Yeah, that's a good question to think about. Is there a transition to a quadratic dependence? We definitely see exactly the cavity pulling. Essentially, we think in terms of line widths instead of Q, but basically the ratio of the atomic transition line width when you include the fact that it's collectively broadened.
Yeah.
Right. The fact that there's some collective stimulation, so NC gamma, compared to the cavity line width kappa. Sets the pulling coefficient when you're very close to resonance. The quadratic, I haven't thought about what that would look like in our system. It's not clear to me where that quadratic arises from. Like, in the end, I'm always convinced there's some simple physics way to understand these things. So there must be a really simple way to understand it. Yeah.
Yeah, I'm pretty sure that there is. I mean, I remember doing it when I was a graduate student. So that means like the middle of the last century. So I don't have a very clear memory of exactly how it comes out, but I do remember that it was simple in the limit of very low atom number. So very far away from mazing.
Yeah.
I think it was a very simple process.
Okay. I will try and think about that, and I'm sure we will see each other
yes,
either in person or virtually at some point, and maybe we can talk.
Right. Okay. Well, I've got other questions, but maybe I should let other people have a chance.
Yeah, and Morgan has his hand raised for quite some time. It was nice to have you here, Morgan.
It's great. It's great to be here. So first, thanks for a great talk. It was super interesting, all the parts of it, and congratulations to your team, especially for the last results on the beyond standard quantum limit atom interferometry. My question, or the most important question to me, is about that last part, and I would like to understand the relationship between the number of atoms that you actually are able to use in the experiment and the techniques that you have to employ in order to get multi-atom coherence, in order to get the squeezing. So my questions are something like, what sets the number of atoms in the current experiment? What could be the limit on the number of atoms in that kind of experiment? And what, if you weren't aiming to do squeezing, could that number be larger?
Yeah. So what I would say is that the number of atoms that we have in our current experiment, or the technologies we have in our lab right now, it's as many atoms as we can get and still run the interferometer well. So we do this velocity selection over here. And it's really set by the fact that the axial temperature of the atoms is some finite axial temperature. So what I mean is, along the cavity axis, the atoms are falling and there's some momentum spread associated with those atoms. And that's what the blue is here. But in order to run our Matterwave interferometer, we really need to have a spread in momentum that's much less than of order 30 kilohertz. That's sort of the sort of spacing between different momentum states. So you can really say I stay in a two-level basis. I stay on resonance and everything can Rabi flop well. So in order to think of two-level physics, I really have to sort of do this narrowing process. That's for the technology we have in our lab, the fact that we've got these thermal atoms. We tried to get more atoms, and then we said, well, we're going to do the physics with what we have. There's no reason that in principle you can't do this with a BEC. And a lot of people have put BECs in cavities. You know, Andreas is here, for instance. And you could basically start with a narrower momentum distribution. You can get a lot more atoms. So I don't think that's fundamental. I do think that one thing that is actually very challenging in any kind of entanglement experiment is the classical control. It just turns out that, you know, what you're asking of your local oscillators to do all these rotations gets pretty hard. So you're asking for a lot of frequency stability. So for instance, if the atomic transition frequency has any noise because of magnetic field sensitivity, your local oscillator has noise on it, either amplitude or phase noise, all that comes into play. And so actually, I think one of the challenges in scaling up is actually just the classical control. We had to learn atom interferometry from scratch. We've never done atom interferometry before. Up to this point in my life, atoms have been little balls. Like, forget this, like, you know, quantum nature of the external wave function. They were balls with magnets attached to them. So we had to build that up. In the future, you could imagine that we could put a BEC in our system and essentially work with more atoms and get more squeezing. I think the squeezing part works. That I'm not so worried about. I'm more worried about the coherent control of it associated with the classical rotations. Did that answer your question?
Well, I had several questions and that answered a few of them, yes. If you put a BEC in, or if one way or another you put a lot of atoms into this experiment, would it change its function in some way? So if you have a cavity optical lattice clock and you put too many atoms in, then eventually they start to see each other, and that changes the clock frequency, and so there's an intrinsic limit to how many atoms you can put in an optical lattice clock. Is there something like that here?
Yeah, this is a great question. So I'm going to make a comment, which is that entanglement, to the best of my understanding, never has a fundamental win for precision measurement unless you also provide a classical constraint on available resources. What do I mean by that? LIGO is using squeeze light now because that's the way to get more sensitivity, but it's actually not fundamental. They could have just built 2 LIGOs, right? Why not build 10 LIGOs? Why not make their mirrors, 100 times heavier? Well, it's because of cost. They had a classical constraint. They had a time constraint on how long would it take to build 10 more LIGOs? The same thing, for instance, people doing axion searches. So Conrad Leonard here at JILA has demonstrated using squeezed fields, microwave fields, to probe a cavity to search for depositing a microwave photons into a cavity associated with axion fields. Okay. There's nothing fundamental there. Like you could have just built like 5 copies of the experiment and done the same, but at some point you go, that costs a lot of money, right? So one of the things I would say is that in general, in order to say where entanglement wins, it's a really tricky problem because you have to define what classical constraint you want to impose in terms of resources. Okay. So if your goal is to build a compact interferometer, maybe this is reasonable. My goal here was to demonstrate that we could even do this at all, that we could pull this off. Okay, as a physicist, I'm happy with that. In the long run, you could imagine that you say, well, I would like to build, a 100-meter tower and build this at Fermilab and launch these into free space. I think that's doable, except one thing I haven't figured out. And that is, I don't know how to do the delta kit cooling. So typically they start with the BEC and then they expand so that they can actually go to relatively low density to do exactly what you're talking about, getting rid of density shifts, getting rid of index of refraction from the atoms themselves, all kinds of funny stuff that happens. So I'd like to take the BEC and actually expand it in space. And they call it cooling, but in reality, it's just an adiabatic transformation of phase space, or not adiabatic, actually, it's pulse. So they basically just, they take the tight confinement and they make it not tightly confined, so they expand in position but they can get more narrow in momentum. Otherwise, if you could tell me how to do that, I think you could prepare 10 to the 6 atoms inside of our cavity in an entangled state. And then you could basically release into free space, do delta kicked cooling, and then run your interferometer. And then you would do fluorescence measurements for the readout step rather than using the cavity for the readout. And Mark has already done that part. He's demonstrated that he can get correlations between, Mark Kasevich, between the squeezing in the cavity and doing fluorescence detection in free space. So I think a lot of the elements are there. It's always going to come down to technology and what are the classical constraints on your system. What are you willing to do and what are you not willing to do for time, money? Maybe there's some fundamental physics reason that you say I'm limited in space. I can't build a 100-meter tower because the physics sits at 1 millimeter. I don't know, but sorry, I wish I could be more clear, but I really think it's a somewhat subtle question of when you win.
Great. Thanks a lot for the answer. I will pass the microphone back to Bill or whoever is next.
Yeah, are there maybe a last question, or are there other questions? Maybe I announce the next quantum seminar next week. We have Anja Jajic from the University of California, Santa Barbara, talking to us about quantum sensing and imaging with diamond spins. So a bit of something else, but also very interesting to us here. Morgan, you still have your hand raised, I assume, so you don't have a new question. And if there are no further questions, then it's...
So if I could be allowed, I do have...
Yeah, of course you are.
Well, actually, I've got lots of questions, but one that was raised by the previous question that Morgan asked about, it's basically about how one does better in this interferometer. Now, if I've understood the interferometer correctly, it's basically a Ramsey-Bourdet Hall interferometer.
I would have called it a Mach-Zehnder, but
yeah,
I'll show it to you. I will get there any second now.
Sure, but I think that's the same as a Ramsey-Bourdet Hall. I think.
Okay, sorry, I'm just the terminology I don't know. That's fine.
Yeah, I mean, what you've drawn looks like two Ramsey. Two Mach-Zehnders. But anyway, if I've understood correctly, you use spin.
It's actually 3, believe it or not, but that's okay. Go ahead.
Okay, but anyway, you use spin squeezing, which produces the kind of improvement that you illustrate there on these block spheres. So it's pretty obvious where the improvement is coming, and the fact that it's done with an interferometer, it's basically necessary because of the fact that you have to take into account the photon recoil when you do this at optical frequencies. If you were doing this at microwave frequencies, it would still be an interferometer, but you wouldn't necessarily have to use that language. But the spin squeezing would work just fine with an ordinary 2-pulse Ramsey process.
That's right. And so, for instance, people have injected already spin squeeze states into microwave clocks and seen improvement.
Right, it works just fine. And this is just extending that into the optical, where you better take care of the photon recoil correctly.
And you're sensitive to inertial effects as a result.
Yeah.
So you open up sort of new physical quantities that you're going to be sensitive to.
Okay, so that's where I'm going with this thing about the sensitivity to other kinds of effects, like accelerations and rotation, or just for that matter, measurements of length. I'm recalling that in order to make a matter interferometer below the standard quantum limit, Murray Holland and Keith Burnett came up with a scheme to do that by putting in squeeze states into the interferometer. And it was very different from the kind of spin squeezing we've got here. So what I'm wondering is, and maybe you've just answered it, is this interferometer with the spin squeezing still going to be sensitive to these inertial kinds of things in the same way that the Holland-Burnett interferometer would be, which uses a very different protocol for getting below the standard quantum limit?
Yeah, so I apologize. I'd have to go back and look at that paper. I'm aware of the paper, but I don't remember the details of the states that they were proposing to inject. I thought it was Dickey states, which I think of as essentially the limit of a squeeze state that has wrapped all the way around the Bloch sphere. So you're really in a JZ equals 0 spin projection state. And then you can just think of it as your squeeze state is that you essentially now your state is a penny. And you flip the penny on edge, it accumulates some phase, you flip the penny back. And if it didn't rotate, when you flip it back, it'll just be in the plane and you'll measure JZ equals 0. But if the penny rotated, when you flip it back, the penny will be tipped up out of the plane just a little bit. And now you'll measure that the JZ is non-zero. It could be +1 or -1, +2 or -2. So you look at the variation of JZ squared.
Exactly, that's exactly right.
In order to pull out the phase, right?
Yeah.
So what I would say is those that kind of interferometry scheme, I think of it as it's when you want to use a squeeze state, but in the limit where you've wrapped all the way around the Bloch sphere. And now you can't just measure spin projection JZ and say, look, on the last part of this diagram here that I'm showing, the very right-hand Bloch sphere, I could say, I'm above the North Pole because the phase took me in some direction. Let me, can you see this Bloch sphere on the right?
Right, yeah.
If that had wrapped all the way around the Bloch sphere, then in fact, I would see that it's a loop and I'd have equal probability for being below. So now I have to measure JZ squared. Of course, I measure JZ on a given trial, but I'd make repeated measurements and then I calculate JZ squared.
Right.
So I just think of it as that scheme is fully equivalent to squeeze state, except in the limit where you've lost track of the sign and you can still pull it out from the variance. Does that make sense?
Yes, but the key thing that I wanted to confirm is that this version, the one that you're showing here in the slide, where it's spin squeezing, this is going to still be equally sensitive to the kinds of things that you want from an atom interferometer, namely inertial effects.
So it's actually amusing. Yes. So for instance, I haven't told you in this, but in a normal Ramsey, you would just say, let's take microwaves, right? I apply my microwaves at 6.834 gigahertz. I evolve for some time and I apply another pulse. Right. And I get the frequency difference between those two, but the 6.34 gigahertz up to maybe some phase jumps, the frequency is just constant.
Yeah.
What I didn't have time to emphasize is that in fact, during this whole interferometer scheme, in fact, this whole sequence, we're actually taking our 2-photon Raman detuning and we're actually ramping the frequency difference as a function of time.
Yeah.
And we're to stay on resonance because the atoms are actually accelerating due to gravity.
Okay.
And so in fact, we pull out from this a measurement of little g.
Right.
Which we know to too many digits because for a time survey, they came in and did some falling corner cubes a few years ago. We know g up to lots of digits. But we're making no claim on being competitive with respect to other interferometers for measuring little g or anything. But yes, we're absolutely sensitive.
Okay, great.
All right. Are there other questions?
I just want to say thanks to James for a great talk, and thanks to Bill for triggering this interesting discussion. That was very entertaining. Thanks.
Good to see you, Andres.
Maybe this was a very nice word at the end. I was very happy to see the sunrise in Colorado.
Yeah, that's right. You can see the mountain now.
Giving a talk. But, I'm convinced now that the Earth is actually round. And, I will tell my All right, then thanks a lot for the super interesting talk and the interesting physics.
Great.
Everybody.
Thank you so much for the chance to come and talk and all the wonderful questions. It was great to discuss. Hope to see everyone soon.
Well, that's for sure. All right, everybody. Goodbye.